Welcome to the deep dive. Today, we're diving into something really fascinating, almost mind-bending. Kakeya sets. Okay, so let's try and picture this. Imagine you're trying to turn, say, a really long ladder inside a really cramped room. It feels like you'd need a lot of space, maybe a circle. But it's trickier than that, isn't it? How the ends move. Well, this basic idea caught the attention of Japanese mathematician Sushichi Kakeya back in 1917. And he asked this really profound question. What's the absolute minimum area you need to spin a line, segment our ladder a full 360 degrees? People guessed maybe a circle or an equilateral triangle. And Pal actually proved for shapes without dents, convex shapes. An equilateral triangle with height 1 was the best you could do, smallest area for that type. But Kakeya himself, he proposed a different shape, a non-convex one, the three-pointed deltoid, kind of like a curvy star. Its area was just pi over 8, tiny. And he conjectured that this was it. The smallest possible area for what we now call a Kakeya set a space where you can continuously rotate that segment 180 degrees.
Right. That was the thinking. Pi over 8 seemed plausible, very elegant. But, and this is where it gets wild, that elegant idea, it turned out to be completely wrong, like spectacularly wrong. Yeah, Besicovitch in 1928, he dropped this bombshell theorem. He showed that for any tiny positive area you can think of, call it epsilon, however small, you can actually construct a Kakeya set with an area smaller than that epsilon, which means there is no minimum area, no single optimal shape like the deltoid.
Oh, hang on. That seems impossible. If you're rotating a real thing, a segment, doesn't it have to sweep out some actual area? How can it be arbitrarily small?
It feels deeply counterintuitive, doesn't it? But it works because of these incredibly clever constructions. One main idea involves something called a Perron tree. You keep cutting and overlapping these tiny little triangles. But the real magic, the thing that makes it work with vanishingly small area, is this trick called pol joins. Think of it like little bridges. They let the line segment sort of teleport between different orientations, different parallel tracks, using an incredibly arbitrarily small amount of extra area to connect the paths. It maintains continuity, but cheats the area requirement.
Okay, teleporting segments. That's pretty wild. So if the area can be infinitesimally small, can it actually be zero? Can a Kakeya set have zero area?
Good question. For a true Kakeya set, where the rotation has to be perfectly continuous, no. That continuous sweep always generates some tiny positive area. But there's a slightly relaxed idea called a Besicovitch set. This is just a set that contains a unit line segment pointing in every possible direction. It doesn't need the smooth rotation, just the presence of the segments. And Besicovitch himself proved, even earlier in 1919, that these sets can have zero area. Now, zero area sounds like nothing, but mathematicians needed a way to distinguish between different kinds of nothing. Like, a point has zero area, but so does a line segment. They aren't the same complexity. So they use something called Minkowski dimension. It's a way to measure how much space a set takes up, even if its area is zero. Think fractals.
Right, dimension instead of area. So that leads to the modern Kakeya conjecture, doesn't it? It's not about area anymore, it's about dimension. Every Besicovitch set in n-dimensional space must have a Minkowski dimension equal to n. So a set in 3D space containing lines in all directions must have dimension 3, even if its volume is 0.
Exactly. That reframes the whole problem. It's trivial for n of 1, just a line. And Davies proved it for n equals 2, the plane, back in 71. But for n equals 3 and higher, that remained one of the biggest open questions in geometric measure theory for, well, decades. A real monster.
And it even inspired related problems, right? Like Wolff's finite-field version.
Yes, the finite-field Kakeya conjecture. Trying to understand the problem in a different setting. That was famously cracked by Zeev Javir in 2008 using this powerful technique called the polynomial method, a huge result in itself. And these sets, they aren't just mathematical curiosities. They have real implications in analysis. They act as counterexamples, showing where our intuitions about how functions behave, like with the Lebesgue differentiation theorem, can break down. They stress test our theories. They also help understand limitations of certain tools used in things like signal processing, these multiplier operators, so they push the boundaries there too.
Okay, but here's the really exciting part. The reason we're diving into this now. Just this past March 2025, a massive breakthrough. Wang and Joshua Azal, they completely solved the Kakeya conjecture for N3.
That's right, a proof for the three-dimensional case.
People are calling it a once-in-a-century proof, just monumental work in geometric analysis.
Absolutely. It's the kind of result that, well, it puts Wang squarely in line for a Fields medal consideration. It's that significant.
Wow. So we went from, a ladder in a shed all the way to the fundamental dimension of space, zero area sets, and now this huge breakthrough. It's quite a journey.
It really is. Shows how simple questions can lead to incredibly deep and complex mathematics. And, this really makes you wonder, now that the 3D case is settled, What happens next? How will these new techniques, these insights from Wang and Zoll, help us tackle even higher dimensions, N4, N5, and beyond? What other connections, maybe in physics or computer science, are just waiting to be uncovered now? That's the big question lingering.